Welcome to lecture 34 on electrical machines 1, and we will start today three phase transformers. And just in my last lecture I told you about one very important test called Sumpner test or back to back test, and this was the picture. So, here the beauty is the transformer under the condition of the test will have rated flux as well as rated current. And if you wish, you can find out the equivalent circuit parameters as well, because you know the no load current of each transformers, you know the wattmeter reading or core loss of each transformer, from which the parallel branch RCL and XM can be calculated, and from this side also you know what is the voltage needed to supply the rated current. Half of that will be actually appearing if you measure the voltage here. If you connect also a voltmeter, I mean suppose you connect also a voltmeter, this is the rated voltage. Similarly, here you connect a low range voltmeter. Okay. So, once again you have generated the short circuit test data. One test as if carried out from the HV side in this particular example, another from the LV side, and equivalent circuit parameters once again can be estimated. And these parameters values will be corresponding to at rated temperature. For example, while carrying out the test, you energize the transformer for a long time, maybe hours, so that the steady state temperature is reached. But it is an interesting test. Now, today we will start three phase transformers. Okay. Three phase transformers. They three phase transformers can be of two types. So, one not two types. One is use three numbers of uh, identical transformers, and in this case when you use three numbers of identical transformers to be used in a three phase voltage transformation, it is called a bank of three phase transformers, a bank of three phase transformer, or a three phase transformer can be manufactured as a single unit. Okay. Three phase transformer as a single unit. Okay. So, we will actually first examine this one, that is three numbers of identical transformers I will take, and the problem is to because our system power system is of three phase. Okay. And in three phase I have three phase voltages, and those voltages will be assumed to be balanced, and if you require to change that voltage to some high or low three phase voltage, then we will be using three phase transformers. That is the idea. That is suppose you have three phase system like this, which is suppose 6.6 kV on one side, then connect a three phase transformer and at the output you will get suppose 440 volt 3 phase. This is 3 phase 6.6 kV, this is 440 volt 3 phase. Of course, 3 phase 50 hertz in our country, and this will be also 50 hertz because frequency remains same. And all these voltages here whatever I have written is line to line voltage. A typical distribution transformer will have, and of course, it will have a KVA rating associated with it. Okay. So, 440 volt 50 hertz 3 phase, and this 440 volt once again is line to line voltage. So, the supply here is A, B, C, and here the supply I may call on the secondary side A, B, C. So, this box will contain a 3 phase transformer, which may use 3 numbers of identical single phase transformer. I must write it like this, single phase. 3 numbers of single phase transformer. Or a 3 phase transformer as a single unit. When 3 single phase transformers you use, it is called a bank of 3 phase transformers. Okay. So, let us start with this. Now, suppose let us assume that I have 3 numbers of single phase transformer, each of rating say 5 kVA, 200 volt stroke 100 volt 50 hertz single phase transformer. This is the rating of each of the 3 transformers I have used. Okay. Therefore, each transformer will have its primary and corresponding secondary. For example, so there are three such transformers. You take 3 numbers, 3 such transformers, 3 such transformers. Now, the moment there are 3 transformers for identifying the primary and secondary coil. So far in single phase there was 1 primary, 1 secondary. So, terminal markings was not that important, although I could do it. It is only HV side, LV side, that is all. But in case of 3 transformers, there will be 6 number of coils. Each transformer will have 2 coils, 1 primary, 1 secondary, 1 high voltage, 1 low voltage. Therefore, it is essential to mark the terminals of the transformer appropriately. So, what I will do is this, suppose this is the transformer 1. Its primary, and this time for convenience I am sketching the secondary of 1 transformers like this. Okay. And I will mark the terminals as A1 and A2. Generally capital letters are used for the high voltage side, and small letters I will tell it is A1, small A2, lowercase letter, and this is capital letter. So, this is 1 transformer, and also I will assume that this this terminal capital A1 and small a1 are dot, and that I know how to ascertain by doing some test. So, polarity test I will do, put the markings. So, this is one transformer, and this transformer I will call transformer A. In the same way, I will have the second transformer, which I am drawing below, B 1 and B 2. You understand now, and its secondary small b 1 and small b 2. And similarly, these two fellows are dots. So, 1 1 are dots, and the third transformer in the same way it will be C 1 capital C 1 capital C 2 and small c 1 small c 2. Therefore, I have very clearly identified the terminals. It looks like I named the transformers in A, B, C, and I will assume it will be supplied from a supply A, B, C. Okay? That is why A phase, B phase, C phase, like that. Acha. This polarity marking is essential, I am telling you. Now, suppose what I will be doing. So, the rating of this winding is 200 volt, this winding also 200 volt rated voltage, and similarly rated voltage of this secondary coils are also 100 volt. This I know, and also I know the rated current of this side as 5000 by 200. I write it here, IHV rated is equal to 5000 by 200, 25 ampere. Similarly, ILV rated will be is equal to 50 ampere, we can calculate. So, rated current of these transformers are also known, rated voltages are known, and I have marked the terminals. Now, what I will do is this, suppose I want to connect the primary coils in star. Okay. Individually I know they are each one these are individual transformers, but as I told you my supply is A, B and C, AS, BS, CS, and I will assume the supply phase sequence to be supply terminals which is a 3-phase system. I will mark as AS, BS, CS, and phase sequence is A, B, C. You understand this. So, this is about the supply. So, this is supply. Now, these 3 terminals A 2, B 2, C 2, suppose I short them, then it becomes a star connected primary. Star connection means 3 coils are there, 3 terminals of each of them you short. Okay? So, this is how you short it. And I will give supply like this, AS I will connect to A1, BS I will connect to B1 and CS I will connect to C1. Now, since it is star connected, the supply voltage whatever it is line to line, that divided by root 3 will appear here. Okay. Since the rated voltage of the transformer is 200 volt, therefore, I can apply a line to line voltage of 200 and root 3 safely, is not line to line voltage 200 root 3 volt. Because after all these transformers are identical transformers, they will have equal parameters. So, root 3 times less voltage will come across the primary windings of each of these 3 transformers. If it is 200, because transformer rating was 200 100 volt, 200 100, therefore, I can apply a voltage of 200 into root 3. So, that rated voltage will then be applied across these coils primary. Secondary coil I have not done anything, they are separate now, nothing has been done. Therefore, this is the thing. Now, let us see what is the phasor diagram of this applied voltage, and let us assume this is the thing. Now, let us see, suppose the phasor diagram of this side is mind you, I have shorted A 2, B 2, C 2. So, this is the point A 2, B 2 and C 2. They are shorted, they will be at same potential. Let this be called A 1, which has been connected to A s. This is same as A s, supply A s. This point is B 1, which is connected to supply B s, and this point is C 1, which is connected to supply C s. S stands for supply. Therefore, this point is the neutral point, I can say. So, A 1 A 2 is the voltage phasor here. The moment and each length here, it is 200 volt, that is why this length is 200 root 3 line to line. Now, the moment you apply like that, this transformer, see the rules of the single phase transformers only we will be using to understand what is going to happen if you connect in a either star or delta, we will see those things. But I am sure about one thing, that the voltage phasor, if it is 200 here, it must be 100 volt and induced voltages are in phase. Therefore, the secondary voltages, if I draw with a different color, it will be half of this length, although I am just drawing A 1 A 2, and it will be parallel to capital A 1 A 2, because induced voltages or applied voltages are all in phase. So, for this single phase transformer, this is what is going to happen, you will get a voltage like this. Similarly, for the second transformer, and mind you, a 3 phase balance system means they are 120 degree apart, is not, lengths are same, supply voltages, these are 120 degree apart. Therefore, B 1 B 2, the second transformer, what is the applied voltage, which phasor is the applied voltage? B 1 B 2. What will be the induced voltage in small b 1 b 2? A line parallel to this, and since b 1 is dot. So, it will be just parallel to this like this. Although, since I have not connected any of this, they are allowed to leave alone. Therefore, there will be a voltage parallel to b 1 b 2. Similarly, there will be another voltage available parallel to this C phase voltage, which will be C 1 C 2. Okay. Then this will be the scene. Secondary coils I have not collected. If you connect voltmeters or see in the oscilloscope, you will find 3 voltages existing across the secondary terminals, which are 120 degree apart, because B 1 B 2 is parallel to this and C 1 C 2 parallel to this. Angle between these two is 120 degree. Here also the angle between these two is 120 degree and so on. Achha. Now, what I will be doing is these 3 terminals I will short. You imagine these 3 are shorted. The moment you short these 3, secondary also gets connected in star. So, this is star connection and then the secondary also becomes star connected. And the moment A 2 B 2 C 2 are shorted, these 3 phasor cannot live in isolation, because A 2 B 2 C 2 I have forced these 3 terminals to be at equipotential. Their potentials cannot be different if it is connected by a piece of wire like this. Therefore, these 3 phasors, this and this cannot now remain in isolation, but what will happen is this it will be like this, that B 1 A 2 is connected to B 2 and C 1 C 2. Are you getting? A 2 B 2 C 2 I have forced them to be at equipotential. These 3 phasors were in isolation, they cannot be. So, it will be like this. So, what I have done? I have applied 200 root 3 line to line voltage here, which will ensure that across each of the primaries of these 3 individual transformers 200 volt appear. Of course, these 200 volt, 200 volt, 200 volt are fine, but they will be displaced by time because of the supply is balanced. And but I know if this is 200, it cannot be, it must be 100, because of the rating of individual transformer being known, 100 is known. And then I draw the primary phasor diagram. Then I have told you A 2 B 2 C 2 are shorted. So, do not leave these 3 phasors in isolation. As per your connection, you put them in, but one thing is clear, A 1 A 2 will be parallel to small a 1 A 2, B 1 B 2 parallel to this one, and this length is 200, this is 100 and so on. That will be maintained, single phase only. See, although we have connected it in a particular fashion, rules of single phase transformers will only I will apply to carry on further. So, this will be the phasor diagram, and then I will say this is a 3 phase transformer which is connected in star star, that I will write like this, and where are the output terminals? Output terminals are here. If you bring it in this way, these will be the output terminals, and I will write here perhaps small a, output 3 phase terminal A, this one is B and this was in C. This is output terminals going to load, going to 3 phase loads. So, it will be like this. Therefore, I have applied 200 root 3 line to line voltage here, What will be the line to line voltage across A 1 B 1? It is this length. Line to line voltage once again will be balanced 3 phase, and the line to line voltage on the secondary side. So, if I write it like this V 1 line to line, if it is 200 root 3, I will say V 2 line to line, small letters for the low voltage side. This will be equal to, each one is 100 into root 3. So, I have been able to change the level of a balanced 3 phase voltage, which is 200 root 3 volt, to a level 100 root 3 volts. That is half I have been able to make. Is that clear? Achha, now, the second thing is, we will discuss. I mean, I will be going a bit slowly, do not worry about that. So, this is the thing. So, I will now draw a bit faster to say about loading of this transformer. For example, what I have done? This is A 1, A 2, this is corresponding small A 1, A 2, these are dots. Similarly, this is B 1, B 2. The previous diagram only I am drawing, C 1, C 2, these are dots, and this is the third phase C 1, C 2, and this is small C 1, C 2. You know? And what connection I have made? I have made this a star connection, and here I have connected 200 root 3 volt 3 phase supply AS, BS, CS, and here the line to line voltage applied is 200 root 3. Why 200 root 3? Because rating of each of the transformer was 200 volt, each one is single phase, 200 volt, 100 volt, 5 kVA, single phase transformer. And rated current of the HV side was 25 ampere, this was 25 ampere rated current, and this rated LV side will be higher 50 ampere 2 times. And what I have done is I have shorted this, and I have taken output here I am so sorry, here I made a mistake, this is B, so A, B and C, these are my output terminal A, B, C, where 100 into root 3 you will get line to line. That is what I have told, I am just repeating this. Repeating this means, now the question is this supply I will connect a balanced 3 phase load. Okay. Here I will connect a 3 phase balanced load. If you connect a balanced 3 phase load, which may be star or delta connected, I do not mind, but only restriction I will put, what is the maximum current I can, what is the maximum line current on the secondary side will be. The LV side rated current is 50 ampere, and it so happens that this current, the line current, because it is star connected, happens to be same as the winding current, LV side winding current. Therefore, maximum current I will allow to flow here is 100 ampere, here also 100 ampere, here also 100 ampere. Okay. And be rest assured, the moment through the dot 100 ampere goes in for this transformer, this fellow will draw 50 ampere. Similarly, this fellow will also draw 50 ampere. This is also 50 ampere. Will these currents be in phase? No, not at all. they will be in time phase difference depending upon the power factor of the load etcetera, but magnitude of the currents will be same. Each one will start drawing oh sorry, this one is LV side I will allow 50 ampere, thank you. So, this is 50 ampere is not, rated current is 50 LV side is this. So, 50 and if it is 50 it will be 25, thank you for pointing out this. So, this is 25, please correct that. So, this is how it will be 25, this is also 25, this is also 25 ampere. So, I have taken 3 numbers of single phase transformer whose rating is this. Now, what is the total KVA? Total KVA will become as a 3 phase transformer, is any side you can calculate. For example, if you calculate from this side, you must be knowing that in a 3 phase system, if the line to line voltage is VLL, if the line current is IL, for balanced thing, the total KVA is √3 VLL IL. Irrespective, it takes care of both star and delta. That is why people love to use this formula so often. Forget about star delta, tell me what is the line to line voltage. Only thing, load is balanced, that is a condition. Line to line voltage is VLL, line current is IL, total KVA will be √3 VLL IL. So, if you calculate from the secondary side, the total KVA then will become √3 VLL is how much? 100 into √3 and IL is 50, is not so much volt ampere, which becomes 15 KVA, which of course will be same if you calculate from this side, which tells you √3, line to line voltage is 200 √3, line current is 25, so much volt ampere, which will also become equal to 15 KVA. Nothing surprising, each transformer was rated at 5 KVA. So, you have connected it as a 3 phase transformer with star connection. Then total KVA will become 15 KVA. Anyway, we will continue with this in the next class. Thank you.